Do we start or we wait for?
We are starting.
We are starting?
So hello everyone. In today's Saturday discussion meeting, Mihir Seth will explain his talk on the Eichler-Shimura relation. Once more, he is revisiting this theory. So Mihir, over to you.
Yeah, okay. Thanks, Devendra. So I'm going to give very basic and rough idea of Eichler-Shimura theory. And what I'm going to follow is the first section of a book called Elliptic Curves by Anthony Knapp. The first section of the chapter on Eichler-Shimura theory, it's chapter 11. And I found it very nice. And I actually discovered this book just 2 days ago. So I didn't get time to read the whole chapter, but I got overview, and I thought it's nice to share this overview with you. Okay, so throughout this program, we have learned that these two objects are essentially the same. So which two objects? So elliptic curves defined over Q. Okay. Consider the set of all elliptic curves defined over Q and up to isogeny. So this set is actually in one-to-one correspondence with the set of normalized eigenform. Eigenforms in the space of weight 2 cuspidal modular forms of level gamma 0 n. With rational coefficients, Fourier coefficients. So it
N should be on the left side also somewhere. No?
Sorry.
N.
Let me finish writing. Okay, so this looks weird now. So I have a set of very nice modular forms of weight 2 with varying level for the congruence subgroup gamma 0 n, but with rational coefficients. And the set of elliptic curves defined over rational numbers up to isogeny. And these two sets are in one-to-one correspondence. And this is the modularity theorem over Q. So what did you ask? There was, Devendra, what did you ask?
N should be on the left side also, some invariant. Gamma 0 n that you are talking here.
That n is not fixed here.
N is not fixed.
Yeah, n is not fixed. N is integer. Yeah, on the right hand side. So okay, so the direction from right to left is what is known as the Eichler-Shimura theory. So Eichler and Shimura attach an elliptic curve to every such modular form. So let's. And the direction from left to right is the modularity theorem, which was more difficult than the right to left direction. So first conducted by Eichler-Shimura and then later proved by Weill-Scaler, Roy, and so on. So this is the modularity theorem, that every elliptic curve over Q arises from modular form. And of course, this one-to-one correspondence is, this is not just any bijection, but the main thing that we want is that the L functions should agree on both sides. So this correspondence satisfies that LES is same as LFS if E corresponds to F. Okay. And okay, so this is the main content of the modularity. And so this part I explained briefly in my talk, in the previous talk, and I will give maybe perhaps more idea today. So okay, so right, so let's consider. Yeah, so that now I mean that's why I said the vertical was better, I think.
Okay, you continue.
Yeah, let me continue this. Okay, so yeah, so let's take a let's take a normalized eigenform with rational Fourier coefficients. Let A be in the space of weight to cost forms as above. Then what was the idea of Eichler and Shimura? How do they attach elliptic curve? So the idea is that you consider so let's call the elliptic curve corresponding to F as EF. The idea to find EF is to look for quotients of the Jacobian of the modular curve attached to gamma 0. So look for quotients of the J0n, where J0n is Jacobian of X0n. That's the modular curve attached to this congruent subgroup, and this quotient will actually come from the modular form that we begin with. Okay, so so now let me recall the Jacobians first of all. So let's say X is a compact Riemann surface. Then Jx, that is the Jacobian of X, is what is this? So first of all, this is so this is defined to be you consider the holomorphic differential forms of X. Okay, so this capital omega holomorphic on X. And then we want to consider the dual space of these holomorphic differential forms. So let's denote this by omega holomorphic X dual, and this dual space of contains the first homology of this topological space X. How? I mean, you know that you can take any cycle, any representative of a cycle in H1, and then you take any differential form and then integrate that differential form over that cycle. You will get some complex number, and that's the map from the differential forms to complex numbers. Okay. Okay, all right. So this is the definition of the Jacobian of X. So clearly, I mean, this is abelian group, but it also has a complex manifold structure. You can view this as complex torus. D-dimensional complex torus. So as abelian group, this is isomorphic to C power G modulo Z power 2G, where G is the genus of X. And this gives the complex structure. So Jacobian of X is also a complex manifold. And moreover, actually, this Jacobian of X is actually a projective variety. That is something not easy. And therefore, this Jacobian of X has a structure of abelian variety, because it's a torus, complex torus, and also projective variety. So there is an algebraic structure which makes it into algebraic group, and it is abelian. So such things are called abelian varieties. So there is a natural map from X to Jx. I mean, after you fix some base point of X, so fix, let's say, X0, X, and then what you do is that you take any small x and map it to this dual form, which takes holomorphic differential form omega to path integration of omega from X0 to X. So and this is independent of the path chosen from X0 to X, because we mod out by H1 of X. So we mod out by the loops basically, so that it is independent of path chosen from X0 to X. So the idea, so as I said that we want to consider Jacobians of modular curves, and we want to construct the quotients of this thing. So this map here from X to Jx is universal, in the sense that if you have any map, any other map from X to complex torus, so this is complex torus. It factors through this map. So that means there exists a map from Jx to that complex torus such that this diagram comes. Okay. So, so constructing the quotients of this thing is sort of it's same as having the map from x to complex towers basically. So what we are going to do is that we will construct a we will actually get this EF uh, together with a map from this modular curve to EF. So this EF will occur as a quotient of x0 in the construction of Eichler-Shimura. So now let me now. So now let's see how we get this EF. Okay, so yeah, so recall that a small f was my modular form. Um, now what I'm going to tell you for the next let's say 10 to 15 minutes, for that I don't need that my cusp form to be eigenform, but for any cusp form would work. So let f be sorry. Let it be in the space of cusp forms, and uh, so the why do we care about only cusp forms? Because the space of cusp forms is naturally isomorphic to the space of holomorphic differential forms on the modular curve. So this is actually isomorphic to the space of holomorphic forms on x0, and the map is Z to x z. Okay. So now using this differential form corresponding to my cusp form, we are going to construct a map from x0 to an elliptic curve. As in we will construct a map to complex numbers, and we will see when the image is elliptic curve. Okay, so right. So let's now let's pick some base point in the upper half plane. So I want to construct a map from x0L, but I will first define a map from the upper half plane, and then we will see that it actually factors through the modular curve x0L. So let's fix tau 0, and then using this differential fz dz, if it, we can define a path integral. So let me define capital F of tau to be the integration from this fixed base point tau 0 to tau over any path of fz dz. Okay. So again, since if f is a modular form, it is holomorphic on the upper half plane. So this integration from tau 0 to tau, it does not depend on the path chosen from tau 0 to tau. So this is a function. F is a function from again upper half plane to complex numbers. Okay, defined as above. Now let's look at f of gamma tau minus f of tau, where gamma is in I found that separate. Gamma is 0. So what is this? So tau 0 to gamma tau fz dz minus tau 0 to tau fz dz. But recall that this f is fz dz is a differential form corresponding to the cusp form on gamma 0. And so it's invariant under the action of gamma 0. It's actually a whole, I mean, differential form on the modular curve. So it leaves on modular curve, not on the upper half plane. So what I can do is that I can what did I do in the book? Yeah. Okay. So yeah, I can write the first part as tau 0 to tau. The sorry. Yeah. So the first part I can yeah. So this is this as tau 0 to gamma tau 0 xz dz plus gamma tau 0 to gamma tau xz dz, and then subtracting the second part, that is tau 0 integration from tau 0 to xz dz. Okay. Now the second part here is actually same as same as this, because xz dz is invariant under the gamma action. So you, by change of variable, this is same as this. So what you get is that the difference of, I mean, f gamma tau minus f tau is actually independent of tau. It is the integration from tau 0, our fixed base point, to gamma of tau 0 acting on tau 0 of the differential xz dz. So this is independent of tau, f gamma tau minus f tau. Okay. So let's call this capital phi of f of gamma. You can actually also check that this is independent of the chosen base point. It's easy. But okay, so I first constructed this function if from upper half to complex numbers, and I found out that f of gamma t minus f gamma tau minus f of tau is actually independent of tau. And now, so let's call this. So it depends only on my gamma and the form f that I began with. So a small lemma is that this phi of f. Now I am looking at phi of f of gamma as a function from gamma 0 n to complex numbers. Okay, is a group homomorphism. So where I look at C as additive group. Okay, so it's very easy. So what is a phi of f of gamma 1 gamma 2 is integration from tau 0 to gamma 1 gamma 2 of tau 0 of xz dz. But I can write this as integration tau 0 from gamma 1 tau. I split this integral from tau 0 to gamma 1 tau 0 in the first part, and in the second part gamma 1 tau 0 to gamma 1 gamma 2 tau 0 tau 0. But now again, since fz dz is gamma invariant, what do we have? So the first part is tau 0 to gamma 1 tau 0 fz dz, and in the second part I can just forget gamma 1 on both sides, on both in the both limits upper and lower, and I get tau 0 to gamma 2 tau 0 fz dz. So which is nothing but 5 EF of gamma 1 plus EF of gamma 2. Okay. Okay, so this difference of is as a function of gamma, it's a group homomorphism. And well, okay, so and now let's say assume that so the image is also a subgroup of C, right? Of course. Now let's assume that the image of phi of f is a lattice in C. Okay. Then what do I have? So then so if I assume this, then what I get is that f of gamma t minus f of f of sorry, no, it was tau, right? Not t. So f of gamma of tau minus f of tau belongs to let's call this lambda. Image of phi is a lattice lambda, belongs to lambda for all tau in upper half plane and gamma in gamma 0 n. So if the image is a lattice, which we know that it's a subgroup of C, but if it is a lattice, then then this f actually is a function from h mod gamma 0 n to C mod lambda. So a priori f was just a function from h to C, but now if it's the image of this phi of f is a lattice, then I get a function from my modular curve x0 n to some elliptic curve. And it's going to be surjective because wait, okay, okay, let's so I get a function and let's so the natural question is when image of f is when is image of phi f is a lattice, or I mean, is it reasonable to assume that it that it can be a lattice? It's right. A priori we don't know anything what is the image, but now the main work of Eichler and Shimura is that, so recall that this phi of f is this makes sense for any f in the space of Kursk forms. But the main point of Eichler and Shimura is that when you take f as a normalized Hecke eigenform with rational coefficients, the image is always a lattice. So that's the main part of Eichler-Shimura theory. Main point is that if f is normalized Hecke eigenform, in S2 gamma 0 n with rational coefficients Fourier coefficients then the image of phi of f in the additive group of complex numbers is a lattice. And that lattice is the corresponding elliptic curve. So in that case, our EF is this C naught lambda. Now, of course, I mean, this is not at all easy to prove. And I mean, it involves the action of echo operators. And I mean, okay, I mean, I don't want to go into details because I don't know much. But as far as I understand from the introduction part of this chapter, we are interested when this image of phi of f is lattice, and which happens only when f is nice eigenform. Now, I want to also discuss one example, which is also discussed in this introduction.
So how that relation comes in?
How?
That relation that you proved in your talk.
Yeah. Yeah, I mean, for that you have to realize this EF as a quotient of the Jacobian attached to x0. And on the Jacobian, you know that, okay, so here is the thing. So Eichler-Shimura relation says that this J0n here, okay, when you go modulo P, where P does not divide this level n, you have that the Hecke operator at P is equal to the Frobenius plus its dual in the endomorphism ring of this Jacobi. So this is the Eichler-Shimura relation, and I mean, the elliptic curve that I told you just now, this EF is it actually occurs as the quotient of the Jacobian J0. Oops. So here I called it AF actually. So this AF is same as that EF. And now you know that these relation hold on this J0, and so they also hold on AF. And they also hold on the corresponding Galois representation, which is nothing but the Tate modulo of this elliptic curve. That's how you get that that the characteristic polynomial of Frobenius is of certain form.
Okay.
Yeah. Okay. So. I mean, an example I wanted to just briefly discuss is the following, which they discuss in the book. So they consider 8 to be equal to 11. So in that case, this x0n has genus 1. And x0. And therefore, this space of cusp forms for gamma 0, 11 is one dimensional. So if you take a normalized, I mean, any non-zero form is an eigenform, and in particular now we consider normalized eigenform. So it looks like the following. So the Fourier expansion looks like this. So f of so so the Fourier expansion looks like this. Q minus square minus Q cube and so on. Okay. So this is my f here, and now I want to convince you that that the map phi of f, the image of phi of f is a lattice, right? Is a lattice in C. This is what we want to show. Okay, so for that, we look at this congruent subgroup gamma 0, 11. It is generated by 3 elements. These are given to be 1, 1, 0, 1, 8, 1 minus 33, 8, 1 minus 4, 9, 1 minus 55 minus. So the first is the translation by 1. Let's call it T, and these, let's say I want this one is 2. Okay. So recall that my phi f was a group homomorphism from gamma 0, 11 to C, defined as you take gamma and send it to integration from some fixed base point tau 0 to gamma of tau 0 of fz dz. So let's look at, so I want to consider image of phi. So image of phi is of course generated by image of T, image of S1, and image of S2. So now image of T is 0. CZ phi f of T is about tau 0, T acting on tau 0, but T is a translation by 1. So that is tau 0 plus 1. So tau 0, integration from tau 0 to tau 0 plus 1, fz dz. Okay, so why this is 0? Well, f is a cusp form. So I mean, so let's. So f has a form of some this e power 2 pi iz minus 2 e power 4 pi iz minus q cube, so that is e power 6 pi iz and so on, plus dot 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 dz, right? And now you just integrate term by term this, since I mean, of course, e power 2 pi I tau and e power 2 pi I tau plus 1, they are the same, they will cancel each other, and there is no constant term because it's a first form. So it's 0. So image of phi is actually generated by just two elements, image of S1 and image of S2. And these are, I mean, okay, this I didn't really understand this. So okay, so the book claims that one can say that these now, let's call them these two images, omega 1, omega 2. These are linearly independent in C, and therefore the group generated by them is a lattice.
Omega 2 are what?
Huh?
What did you say? They call it?
Yeah. Let me write it. Omega and omega 1, omega 2 are linearly independent. So one has to do. I don't know why this is true, but I think independent in C, and therefore the image of phi is a lattice. I mean, this is the main point actually to show that it is a lattice.
Omega 2 are the two periods.
Huh?
Omega 2 are the two periods.
Two periods.
Period generate the lattice, right?
I mean, yeah, the omega 1, omega 2 are the images of these two group elements under this phi of F. Under this group homomorphism. And I think, I mean, there are some explicit computations to do to show that these are linearly independent. But I mean, if you have, I don't know if you have this book, but if these are done on page 305, I mean, they just write that these are independent over R, and therefore define a lattice. So anyway, so let's assume that let's assume that these are linearly independent and they define a lattice. Then in this particular example, what do we have is that
I think this example was initially by Eichler, and he has some curve also, right? X cube or something.
Particular example was initially by whom?
Eichler.
Oh, is it? I don't know this.
So he gives the equation of the elliptic curve also?
Yeah, so the advantage of this is that you can find equation of this elliptic curve. So
X cube minus X something?
yeah, so yes, the equation looks as follows. This is what you had in mind?
Yeah, something. I think this was done by Eichler only.
Oh, so okay, I see. I haven't seen that paper, his original paper. Okay.
So here we have some advantage of curve being genus 1 and
yeah. I mean, here it's.
But if you want to generalize this theory to general thing, computations would be much harder.
Right. So in
understanding why things happen.
When you don't have genus 1, this space of holomorphic differential forms
is also one dimensional.
You consider the Hecke eigenbasis of this space of differential forms or the space of cusp forms, and for each fi in that basis, you define this phi of fi, which I did here only for one f because it is not dimensional. Yeah, so right. So actually, the idea of attaching elliptic curve to a nice cusp form is that you consider the space of differential forms, which is then look at the Hecke eigenbasis. Now each cusp form in that eigenbasis will give rise to some quotients of the Jacobian, and not all of them will be elliptic curves because because to have a elliptic curve you need that all the Fourier coefficients are rational numbers. So, but one of them will be an elliptic curve, and that is the EF you consider.
I see. So here you have only one element in the basis, so it came out exactly that elliptic curve, right?
And also if to begin with f itself, my f, you see f has Fourier coefficients or integer. It is important that the f must have rational coefficients. Yeah, q to 1 minus 2 minus 1 2. Okay, and once you have elliptic curve attached to modular form, then how do you get a Galois representation? You just take the Tate module attached to elliptic curves at various primes. This I discussed in my talk, right? Once you have elliptic curve, the desired Galois representation is VLAF, where VLAF is the so here is the thing. It's the inverse limit of all L torsion points of that AF or EF. That is that has the action of the absolute Galois group of Q. That's the Galois representation attached to modular forms. I mean, from modular form you get elliptic curve, and from elliptic curve you get Galois representation.
So yeah, so this Galois representation getting from that particular EF elliptic curve is the standard procedure, right? Looking at the
Galois representation comes from AF and what?
You got the EF first from the modular form.
Yes, EF.
And
you
then
first
by the
get EF from F, and then you get Galois representation. I mean, from EF, which is the Galois, which is by definition is the Galois representation attached to cusp and cusp eigenforms.
Okay.
And why do we have this equality, the equality of L functions? This is because oh yeah, that is also important. That this EF you get is yeah, and I did not like this is the main point actually. So the EF the main properties of the EF. property of EF is that AP of EF is equal to AP of F. I think for all the non-dividing the level. And what is AP of EF? This is by definition P plus 1 minus the reduction of E at P, which is exists because P does not divide. So the reduction is E tilde F, and you take the rational points of this E tilde F, that is. So this E tilde F is a elliptic curve defined over FP, and you look at the number of rational points of E tilde F, and then subtract that from P plus 1. Then this is this quantity AP, and this is the main property of this elliptic curve, that it matches with the Fourier coefficients of the.
And what would be the exact Galois representation in this example? Exact Galois representation in this example?
Exact Galois representation.
For this particular thing. It might be given in that book, right?
I mean, you want to know how the Tate model of this elliptic curve look like, right? But what do you mean by looks like? Is in
you constructed that formula that day, na?
Which formula?
Eichler-Shimura relation.
No, I don't understand what
to prove the Eichler-Shimura relation that day, na, I am asking ki how that would look like in this example. TP factorizing and
how would that look like? What does that mean? This holds for any example, but I mean, like sigma p. I don't understand how it looks.
So this Tate module that you constructed.
Okay, you want to understand what this representation is. But what do you mean by to understand
particular example?
No, I mean, okay, I understand. So you want to know what this representation is, but it is same as asking what is the characteristic polynomial of the Frobenius at unramified points.
Yeah, those things, yeah. It is given in that book, norm book.
No, but that comes from this. That comes. I mean, the characteristic polynomial is this, right?
Here it is general theory, na. So I'm just saying for
but yeah, then just so I mean, you know what this is, what APs are like. APs are these coefficients, and then you know what this characteristic polynomial is.
Okay.
For any value.
Okay, good.
Yeah, I think
one point was the point of thinking. Their details. Like if you go to the above in the slide.
Slide.
A little bit above more. Where you are showing the theorem. Here, this point, main point.
Yeah, the main point is that
it requires some
is lattice, and that's what about that?
I'm asking it requires more work, right?
Yeah. I mean,
okay.
I mean, I gave you some idea in the talk, right? How do you get EF as a quotient of the Jacobian, and actually that is. So, I mean, this involves that constructing quotients of Jacobians, the Hicks operator action. So you consider the Tate algebra, this P, and then you get a ring homomorphism from this big Tate algebra to C attached to this modular form, which takes each operator to its eigenvalue. when we look at the kernel. But again, I can say what is happening, but I don't know why this works out, or what's the intuition behind this.
Okay.
Okay, so can I, do we have like few minutes?
Yeah, we have, I think, 5 minutes.
There is a nice YouTube video, sort of, but maybe I don't know if you have watched it or not, but I can share.
I think.
Yes.
Yeah, I have seen it.
You have seen?
Imagine this scenario.
I have seen
You
it.
buy a little known cryptocurrency at $2.82.
You have watched it?
Yes, I have watched it.
Okay, then I thought I would maybe.
Yeah, but you can send me the link once again.
Huh?
You can send me the link once again on WhatsApp, maybe.
Okay, this is very, again, very basic, but it sort of
Gives the idea.
gives some idea of what is happening. And actually, I was very surprised that this came just 2 days ago, and I thought I would.
Maybe you run the video, Evans.
Hmm?
Run it, the video.
In 1916, the mathematician Ramanujan looked at the following very strange function, which he called delta of q. Q times 1 minus q times 1 minus q squared times 1 minus q cubed, and on. And then all of this raised to the 24th power. For no particular reason, he decided to multiply it out. And when he did, he got this strange sequence of numbers. While most people wouldn't have looked twice at this list, Ramanujan noticed something very strange. If you took this number and multiplied it by this number, it equaled this number. Another observation: if you wrote out some more coefficients and you took this number times this number, it equaled this number. In other words, the coefficients of this function were multiplicative. The nth coefficient times the mth coefficient equals the nmth coefficient, whenever n and m were co-prime. Ramanujan himself didn't know how to prove this, and he conjectured it in what is now a very famous 1916 paper. What we now know is that Ramanujan's identity is reflective of the fact that these are no ordinary numbers. They actually contain some very deep meaning. In this video, we'll see what the true meaning of these numbers is, and how they form a bridge between number theory and complex analysis. We'll then see how that bridge leads to the proof of Fermat's last theorem. In a bit more detail, that's because the function that Ramanujan discovered is not alone, but actually belongs to a very huge family of functions that we now know are very deep. The numbers that appear in their coefficients have an interesting hidden meaning. These are functions that we call modular forms. This video is an intro to what modular forms are and how they proved Fermat's last theorem. For the sake of concreteness, I'll focus on this one here. Our story begins in the 1950s with mathematicians Martin Eichler and Eichler-Shimura. They looked at the coefficients of this modular form and wanted to understand their true meaning, so to speak. The first key step was to visualize this function in the complex plane. Here the variable q is a complex number in the interior of the unit circle in the complex plane. To find the true meaning of the coefficients of the modular form, they took a curved arc in the circle and integrated the modular form over that curved arc. That is, they added up the values of this function over the arc. That gives you a complex number. Let's plot that over here on the right. Now take another arc in the circle and integrate the function over that arc. That gives you another complex number. Let's plot it on the right. Now do that for more and more arcs in the circle. Slowly, you notice that a pattern starts forming on the right. The values on the right form a lattice in the complex plane. The next insight is that this lattice has a very deep connection to number theory. To see it, it might be helpful to look at one dimension lower. Suppose that you have a one-dimensional lattice, just a bunch of evenly spaced dots on the number line. How do you relate this lattice to something that lives in the world of number theory? Well, you can do the following thing. Take a function that repeats in every portion of this lattice. So what we've drawn is the sine function. It's periodic. Then, set the variable x to equal sine of t, and set the variable y to equal cosine of t. And notice that they satisfy the following equation. X squared plus y squared equals 1. So we started off with a lattice and ended up with an equation, which lives in the world of number theory. What we'll do now is an analogous process in higher dimensions. Given this lattice, we'll look at a higher dimensional analog of sine, which repeats in every square of the lattice. The function you're looking at right now is called the Weierstrass p function. Set x equal to p of z, and y equal to p prime of z. Then x and y satisfy this rather complicated looking equation. So just like before, we started off with a lattice, and we cooked up something which lives in the world of number theory, an algebraic equation. Now this equation over here is given a fancy name. It's called an elliptic curve. Let's summarize what we've done so far. We started off with a modular form. From it, we cooked up a lattice. And from that lattice, we produced this equation over here, an elliptic curve. But we started off the video wanting to know, what is the hidden meaning of the coefficients of this modular form? The point that we're leading up to is that they are exactly reflected in the number theory of this elliptic curve. But how is that so? Well, in the world of number theory, a standard question people ask when given an equation is the following. How many solutions are there to this equation mod p, where p is a prime number? For example, if p equals 5, then the pair 4, 1 is a solution mod p. That is, if you substitute x equals 4 and y equals 1, you'll see that the two sides are congruent mod 5. Similarly, one can check with a brute force search that there are 4 solutions to this equation mod 5, listed here. We can do this for every prime number p. So for every prime number p, we can count the number of solutions to this equation mod p. For p equals 2, there are 5 solutions. For p equals 3, there are 5 solutions. Likewise, you can fill this out for all primes p. Now, this list of numbers doesn't look too interesting at the moment. Here comes the magic. Instead of considering the number of solutions mod p, consider this slightly weirder thing. 1 plus p minus the number of solutions mod p. Here are the updated numbers. The point is, these numbers exactly match the coefficients of our modular form. For example, the number here is -2, and the second coefficient of our modular form is -2. The number here is -1, and the third coefficient of the modular form is -1. Likewise for all the other numbers. We started off the video saying that the coefficients of a modular form have a hidden meaning. We can now see what this is. These coefficients somehow count the number of solutions to an algebraic equation living in an opposite corner of math. They have a strange predictive power. In other words, we have two worlds, modular forms and elliptic curves. What we've done is, to a modular form, we've attached to it an elliptic curve. But it wasn't until many years later that people dared to suggest that you might be able to go back, that maybe every elliptic curve came from a modular form. Now when you first hear this, a reasonable reaction is that it seems very unlikely. But in 1967, this feeling was formalized into a conjecture that became known as the Taniyama-Shimura conjecture. Every elliptic curve over Q is modular. That is, for every elliptic curve over Q, there is a modular form whose coefficients are essentially the number of solutions mod p to this elliptic curve. Now the trouble with this conjecture is that nobody knew how to begin attacking it. John Coates, a very well-known number theorist, said, "Beautiful though this problem was, it seemed impossible to actually prove." And then 20 years later, the stakes were raised even higher when Frey, Serre, and finally Ribet showed that the Taniyama-Shimura conjecture implied Fermat's last theorem. There was a joke at the time that this was reducing one impossible problem to another equally impossible problem. But unbeknownst to the rest of the math world, somebody had been working in secret to prove the Taniyama-Shimura conjecture for 7 years, and in September 1994, Andrew Wiles announced that he could prove enough of the Taniyama-Shimura conjecture that Fermat's last theorem would then follow. Specifically, he proved the following statement: every blank elliptic curve over Q is modular. The blank over here is an adjective, semi-stable, and it was known that this statement was enough to prove that Fermat's last theorem was true. Slowly, in the years after, people started removing conditions on the theorem. So the Taniyama-Shimura conjecture was then proven for all curves that were semi-stable at 2 and 3. Then it was proven for all curves satisfying an even weaker technical condition. And then in 2001, the full conjecture was proven by Breuil, Conrad, Diamond, and Taylor. And thus, a theorem that first seemed impossible to attack just 40 years later was completely solved. That's all for this video. With that, thanks for watching, and I'll see you next video.
Yeah, so I mean, this video captured exactly what I wanted to say.
Yeah, thanks.
Thank you.
So, shall we close, Mihir?
Yeah.
Okay, thanks for this nice presentation and explaining things.
Oh, you are welcome. I hope I.
Complimented your talk actually very well.
Okay, thanks. Yeah, I mean, one has to work out all the details. Otherwise, this
details
is.
are a lot.
Huh?
Details are there much lot.
Yeah, there is a lot of. Okay.
Okay, see you.
Yeah,
Good
see you. Bye.